properly verify ground faults before powering up a 480-volt system, you'll need some materials. Firstly, an insulation resistance tester, sometimes called an IR tester, with a range of 500 volts to 1000 volts. Secondly, test leads with alligator clips. Now follow these steps. 1. Disconnect all power sources. Turn off the circuit breaker or disconnect the power cord. 2. Lock out and tag out the power source to prevent accidental energization. 3. Prepare the insulation resistance tester. Set the tester to the desired voltage, typically 500 volts or 1000 volts. 4. Connect the test leads. Attach one lead to the system ground terminal or known ground point. Then attach the other lead to each phase conductor, L2 and L3, one at a time. Ensure good electrical contact by using alligator clips. 5. Perform the insulation resistance test. Start the test and record the resistance reading for each line to ground connection. 6. Evaluate the results. If the insulation resistance is greater than 1 megohm, that's 1 million ohms, the system is considered well insulated. A reading below 1 megohm indicates a potential ground fault. Here are some additional tips. Firstly, test all 3 phases to ground and phase to phase to ensure thorough verification. Secondly, if a ground fault is detected, isolate the faulty component and repair or replace it before powering up the system. Thirdly, use anti-short bushings or other protective devices to prevent accidental ground faults caused by wire damage. And lastly, always follow proper safety protocols when working with high voltage equipment. The insulation resistance tester, often referred to as a megometer or IR tester, is a crucial tool for assessing the integrity of electrical insulation. Unlike a standard ohmmeter, which uses a low voltage source, an insulation resistance tester applies a high direct current, DC voltage, typically ranging from 500 volts to 1000 volts or even higher, to measure the resistance of insulation materials. This high voltage is necessary to effectively stress the insulation and reveal any weaknesses or potential faults that might not be apparent at lower voltages. The principle behind insulation resistance testing is quite straightforward. The tester applies a known voltage across the insulation and measures the resulting current flow. According to Ohm's law, resistance is equal to voltage divided by current. So the tester calculates the insulation resistance based on these measurements. A high resistance reading indicates good insulation, meaning that very little current is flowing through the insulation material. Conversely, a low resistance reading suggests that the insulation is compromised, allowing more current to leak through, which could indicate a ground fault or other insulation failure. When using an insulation resistance tester, it's important to follow proper safety procedures to avoid electrical shock. Firstly, always disconnect the equipment from the power source before testing. Secondly, use appropriate personal protective equipment, PPE, such as insulated gloves and safety glasses. Thirdly, ensure that the tester is properly grounded. And lastly, never touch the test leads while the tester is in operation. There are 2 main types of insulation resistance tests. Firstly, the spot reading test, and secondly, the time resistance test. The spot reading test involves applying the test voltage for a short period, typically 1 minute, and recording the resistance reading at that point in time. This test provides a quick snapshot of the insulation's condition at a specific moment. The time resistance test, also known as the polarization index test, involves applying the test voltage for a longer period, typically 10 minutes, and recording the resistance readings at multiple intervals. This test provides more comprehensive assessment of the insulation's condition by evaluating how the resistance changes over time. A good insulation will exhibit a gradual increase in resistance over time, indicating that the insulation is becoming more polarized. A constant or decreasing resistance may indicate moisture contamination, degradation, or other insulation problems. When interpreting insulation resistance test results, it's important to consider the equipment's operating voltage, temperature, and humidity. Higher operating voltages require higher insulation resistance values. Higher temperatures and humidity levels can reduce insulation resistance, so it's important to take these factors into account when evaluating the test results. As a general guideline, insulation resistance values of at least 1 megohm are considered acceptable for most electrical equipment. However, specific equipment manufacturers may have their own recommendations for minimum insulation resistance values. Therefore, it's always best to consult the equipment's instruction manual or a qualified electrician for guidance. If an insulation resistance test reveals a low resistance reading, it's important to investigate the cause of the problem and take corrective action. Common causes of low insulation resistance include moisture contamination, dirt and debris accumulation, insulation degradation due to aging or overheating, and physical damage to the insulation. Depending on the cause of the problem, the corrective action may involve cleaning and drying the insulation, repairing or replacing damaged insulation, or replacing the entire piece of equipment. In addition to testing insulation resistance, it's also important to perform other electrical tests such as continuity tests and voltage drop tests to ensure the overall integrity of the electrical system. Continuity tests verify that electrical circuits are complete and that there are no open circuits. Voltage drop tests measure the voltage drop across various points in the circuit to identify any excessive resistance or other problems that could affect the performance of the equipment. By performing regular electrical testing and maintenance, you can help prevent electrical failures, reduce downtime, and improve the safety and reliability of electrical systems. Regarding anti-short bushings, these are small, insulating components designed to protect electrical conductors from abrasion and damage where they pass through metal enclosures or fittings. They are commonly used with metal-clad MC cable and armored cable AC to prevent the sharp edges of the metal jacket from cutting into the wire insulation. Anti-short bushings are typically made of plastic or other insulating materials and are available in a variety of sizes to accommodate different cable sizes and conduit sizes. When installing anti-short bushings, it's important to ensure that they are properly seated and secured to the cable or conduit. The bushing should fit snugly against the edge of the metal enclosure or fitting to provide adequate protection for the wires. It's also important to use the correct size bushing for the cable or conduit being used. Using an undersized bushing may not provide adequate protection, while using an oversized bushing may allow the cable or conduit to move around and become damaged. While anti-short bushings are effective at preventing abrasion and damage to wire insulation, they are not a substitute for proper wiring practices. It's still important to carefully route and support electrical conductors to prevent them from becoming damaged or stressed. It's also important to avoid over-tightening connectors and fittings, as this can damage the wire insulation and create a potential electrical hazard. In addition to anti-short bushings, there are other types of protective devices that can be used to prevent ground faults and other electrical problems. These include ground fault circuit interrupters, GFCIs, arc fault circuit interrupters, FCIs, and surge protectors. GFCIs are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. FCIs are designed to protect against electrical fires by detecting arc faults, which are caused by damaged or deteriorated wiring. Surge protectors are designed to protect electrical equipment from voltage surges, which can damage or destroy sensitive electronic components. By using a combination of protective devices and proper wiring practices, you can help ensure the safety and reliability of electrical systems. It is also important to note that while the initial ohmmeter test didn't reveal a fault, this is not uncommon. An ohmmeter uses a very low voltage, often less than 9 volts, to measure resistance. This low voltage may not be sufficient to break down weak or compromised insulation. The insulation may appear to be intact under this low voltage, but when subjected to the higher voltage of a 480 volt system, the insulation can fail, leading to a ground fault and the subsequent events you described. That's why using an insulation resistance tester with a higher voltage is crucial for identifying potential weaknesses in the insulation before energizing the system. Furthermore, the location of the fault, a nick in the purple wire caused by the MC connector, highlights the importance of careful installation practices. Even with the use of anti-short bushings, improper handling or installation can still lead to insulation damage. It's essential to inspect wires and cables for any signs of damage during installation and to ensure that connectors and fittings are properly tightened to avoid stress in the insulation. Another factor to consider is the type of insulation used on the wires. Different types of insulation have different resistance to abrasion, heat, and chemicals. If the insulation is not suitable for the application, it may be more susceptible to damage and failure. In addition to the insulation resistance test, there are other diagnostic tests that can be used to assess the condition of electrical equipment and identify potential problems. These include infrared thermography, which can detect hotspots caused by loose connections or overloaded circuits, and vibration analysis, which can detect mechanical problems in rotating equipment such as motors and generators. By using a variety of diagnostic tests and maintenance techniques, you can proactively identify and address potential problems before they lead to equipment failures and downtime. Ultimately, preventing ground faults and other electrical problems requires a comprehensive approach that includes proper design, installation, testing, and maintenance. By following established safety procedures, using appropriate protective devices, and performing regular inspections and testing, you can help ensure the safety and reliability of electrical systems and prevent costly equipment failures. Remember that working with high voltage electricity can be dangerous. If you are not qualified to work on electrical equipment, it's best to hire a licensed electrician to perform the work. It's always better to be safe than sorry when it comes to electricity.